Hello everyone, can you hear me? Yeah, sounds like you can. So hi, welcome. First of all, just some formal stuff. We'll be using slido.com because this session will be a bit interactive. So if you want to join us and want to vote on when this journey will take you, please go to either slido.com and enter the hashtag #CheVoteDL or use the QR code. There will be 3 polls in general, I think. And each of the poll will also have the QR code so you can scan it. So we'll give you like some time to have a look at it. If you do have some knowledge or experience with deep learning, please go to the Slido and help us guide this talk. So what is the plan for today? We'll have a short introduction, and then we'll have the first part of the talk, which will be the practical tips for deep transfer learning for about an hour, and then we'll have a talk by our colleague about the cooperation with students and some time for question and answering, again, through the Slido. So first of all, let us introduce ourselves. So my name is Martin. Hi. I'm part of the H2O for the last 5 years. I'm also an current H2O employee, but I'm ex-FIT student, as well as Adam over here. So thank you. Especially thank you, former dean, for this very nice institution. So what we do is we're data scientists, me and Johan, and we have Adam over here, who's a machine learning engineer. We compete on Kaggle. I am currently ranked number 800, so nothing groundbreaking, but we have Johan over here, and I'll pass the microphone on.
Yeah. Hey everyone. I'm also with H2O for almost 4 years already, and I'm working in the Prague office for this time. And my main focus there is deep learning, specifically for computer vision. And I'm also, as Martin mentioned, participating in some Kaggle competitions, and I'm Kaggle competitions grandmaster, and currently I'm in top 10 in the global ranking. And I used to work in different domains, but currently my focus mainly in deep learning, and today we'll try to share our experience, our practical experience of tuning their deep learning models.
Yeah. Hello, my name is Adam Valenta, and I am machine learning engineer on our open source project at H2O AI. And I will be speaking as last. I'm currently 2 years in the company, and I would like to break down my journey from CTU into the H2O, and that will be our last part of the presentation.
So some quick words about H2O, which is the company we work at. It's a company started in Silicon Valley at 2012. It currently has 326 people. Out of those, roughly 10%, so 31 people are currently employed in either Czech Republic or Slovakia. We only have office in Prague. The rest of the people are working from home. And so what do? We try to build tools for data scientists, and we try to build tools to help everyone use and leverage the AI. So our motto is we are democratizing AI. And so first of all, how do we do it? And how do we know that our tools are good? So I don't know if everyone here is familiar with Kaggle or not. It's a platform where you compete. So it's a data science competition website where you compete for money, monetary prizes, and some ranks. And we employ currently 5 people from the top 10 worldwide ranking, and Johan is actually one of those people. And so we have these best people, and they try to build, or they do build some of the best software that we have. And we challenge the software, we challenge all the new algorithms, approaches, and we try to see like how that fits all the other competition. So yeah, we have 222 of the top 500 Fortune customers. We deal with a lot of famous and known banks and other companies. And what do we offer? So we offer, and what have we worked on, right? So we build solutions for data scientists. We have AutoML solutions, machine learning solutions. We are building, Johan and I are currently working on deep learning solution, or solution for automated deep learning. But we do more than that. We also look into model interpretability, model deployment. So we try to cover all the life cycle of dealing with data, creating models, deploying them, maintaining them, tracking them, and also like leveraging them and having some added value from this process. So we have a thing called H2O Cloud, where we have all these things packaged into different separate applications. And now let's start with the actual talk. So I'll pass on the microphone.
All right. So we will split this talk into kind of different blocks. So we prepared some live demo, and we will make some live experiments during the talk. And also we will cover, once the experiments are running, we'll also cover some theoretical basis of what we are doing. And the first term I'd like to discuss is this transfer learning. So it was in the title of the talk. And the idea of transfer learning is pretty simple. So firstly, we take some kind of large database of data. We train some models on this large database. And afterwards, we apply this like models that was trained before on our small data set. So the advantage here is that you don't need to have a large data set to obtain good models. But what you can do is you can utilize their data that was collected before, pre-train the models on it, and then like fine-tune. It means to train for a shorter time period, and you can already obtain pretty good results. And the larger the data set you have trained it before, the better the results you might obtain, even if you have like 100 of examples of images or text, for example. And today we'll be doing this transfer learning on a particular task. And what we will do is we will build an image classification model, and we will do it together. So initially, we also created this model in-house. So we ran some experiments ourselves and did it like in a way how we would tune these parameters and to obtain the best performance of the model. And today, we will ask you to also vote and select the parameters that you would like to tune. And in the end, we will compare the results of like our model and the models that you will train today and see what was a better strategy. And here we assume that we already have a framework, so we'll be using a framework called Hydrogen Torch that Martin will introduce in the next slide. And this is our internal tool for training deep learning models. So it means that you don't need like to code or whatever. So we'll just like select some options, and it is the UI where you can select different hyperparameters and train the models. And also another thing that we assume is that we have kind of like a robust cross-validation strategy. It means that we have a good strategy to evaluate our models and compare them. And firstly, we'll use like random k-fold for the validation. And in the end, we also have a holdout set with their test images that model like hasn't seen during the training. This will be done on a small subsample of their like product's 10K dataset. So the dataset is their image dataset with their photos of some e-commerce products that were taken by actual users. And we have 20 classes, and like the distribution is uniform, right? So we have like 100 examples for each class. And as I've mentioned, we have like 2,000 train examples and 1,000 test examples that we'll test in the end and compare our models. And for the metric, we'll be using F1 score that combines like precision and recall in a single metric. All right.
Okay, so I will introduce the Hydrogen Torch. What does it look like, just so you are familiar with the tool? Let's see. Hopefully it will load, which it should, if we do our job well. Okay, so it's a tool where you upload your data and you can create experiments, right? So first of all, let's have a look at the data set. So we have our data set loaded in, and we can see what kind of data there is. So we have a bunch of photos. Each photo is associated with a different group. So each photo has a group ID linked to it, and this will be our target. So we will try to predict which group does each photo belong to. Yes, so we don't really know what these groups are, but there might be something like toys, maybe jewelry, paintings, and other categories. Okay.
Yeah, all right. And here is their kind of very simple scheme of how the usual process of tuning machine learning models look like. So firstly, we build some baseline model. So usually you don't go and like utilize all the like super crazy architecture, super crazy parameters and build in some hard model. So usually we start with a very simple baseline model to just get a feeling about the data set and get some kind of like approximate performance of a very simple model. And then there is kind of like infinite part where there is a cycle where we'd like to tune the hyperparameters. And the idea of the hyperparameters is different settings of the model that you can adjust. And depending on the results, you might think that it works or doesn't work for a particular data set. And then you can repeat this process. So basically it's just iterative process where you kind of like start with some kind of set of baseline parameters, and then you just change them and iteratively try to find the best set of hyperparameters. And once you are happy with your results, with your model, you can go ahead and deploy this model to the production and use it in the production setting. And today we'll be concentrating only on these three first blocks, right? So we'll concentrating only on this part where we have some baseline model, and then we'll try to tune the hyperparameters for this baseline model to obtain the best model in like 30-40 minutes that we have today. We'll not touch this deployment part for today. And yeah, as I've already mentioned for the baseline model, that it is usually better to start as early as possible with a baseline model and just to get a feeling of the data set. And it will also allow us to iterate faster. So usually baseline model is pretty small with some small images, with some small architecture, and it allows us to run more experiments for a single like amount of time. And that is why it is usually some pretty quick experiment. And apart from that, we are also like assuming some things that we will fix for this kind of like setup today. So first we will be using pretty like large machines. So it has like 3 8000 GPUs with 48 gigabytes each. So it is pretty heavy GPU. So all the experiments will be pretty quick. Then we are also fixing their loss to be cross entropy. We are fixing the batch size to be 32. And we are also there fixing the optimizer to be AdamW, and we will not tune them. So we're just assuming that these settings are good enough, and we will not tune them today. And another thing that we do not tune today will be learning rate scheduler. So yeah, if you go to the next slide, it is a learning rate scheduler that we will use. So it is like a sign decay learning rate scheduler. We will start with some like particular value of learning rate, and then during the training process, we are gradually decreasing it towards the 0. And the advantage of this approach is, firstly, that it is not constant, right? So it means that closer to the end of the training, the learning rate converges to the lower values, and it means that during the end of the training, like there will be no like large jumps of the learning curve. Another advantage is that we are not doing early stopping here. So if you're familiar with early stopping, it is the idea of picking up the best epoch during the training, or to pick up the best iteration during the training and use it as like kind of your best model. However, the problem here is that it is kind of like over-optimistic towards your validation set because you're overfitting to this early stopping. So basically, you're just picking up the best epoch that might be very different for your test data set. And that is why you're overfitting to validation data set. And in this setup, what we'd like to do is we'd like to build such models that achieve the best performance in the very end. So we'd like the model to converge to the best values in the very end, and that is why we'll be using this scheduler. All right, and here we will now discuss the baseline model.
Okay, so some information about our baseline model. So we started with a model that whatever images you put into it, we will resize them to 224 by 224 for a backbone. So if you're familiar with backbones, if you're not, this is the name of the architectures. So we'll be using efficient net v2. And there are different sizes to it. So B0 is the smallest one. And as we said, this is our baseline model. So we'll start with the smallest. We'll have fixed batch size of 32. Then we'll choose the learning rate at 0.001. And we'll train for 5 epochs. In case of computer vision models, you can also do augmentations. So we'll only do the basic augmentations, which is horizontal flip. Some typical hyperparameters to tune, and this is not in the order of importance. That's actually what we will have a look into together. So the hyperparameters to tune are usually the backbone family. So in this case, it was the efficient net. It could be VGG, it could be ResNet, or whatever other fancy architectures you're familiar with. Then it could be the backbone size. So in case of efficient net, it's the B0, 1, 2, 3, up until 7, I believe. Then there's different kinds of poolings you can have. You can have a dropout, which shows which does some regularization, number of epochs for how long you train, learning rate, which is the size of the step you use during training. Then your regular augmentations, which are like flipping, shifting, different saturation, and so on, or mixed augmentations. We'll discuss those today. And you can change the image size. So now we would like you to choose which you think are the best or the most important hyperparameters. So if you could join the slido.com, then you can select all the hyperparameters. You don't need to select all of them. You select them in order of priority. And once you're happy with it, just please write submit. We'll wait for a while so that these results should be updated live. So let's see how good you are, guys. We have 6 participants ranking. I would tell a joke meanwhile, but I'm really bad at telling jokes, so sorry about that. Okay, seems like this is pretty close race. Okay, so let's have a look at the current results. So it looks like learning rate is the most important based on your knowledge or feeling. Then the backbone family, number of epochs, spoolings, backbone size, and an image size. So let's see how close you guys were to what we think is the right answer. Right. Okay. So first we can start the experiments based on your suggestions. So we'll start with what? With 2 first things. So the learning rate and backbone family. Okay. So let me go to our tool, H2O Hydrogen Torch, and now we'll create an experiment using our data set. Yeah, so first we will have a look at our baseline experiment, which we already created. So we are using F1 as a metric. So the validation F1 for our baseline experiment is 0.795. And we were able to train it, the baseline model, in 23 seconds, I believe. So now let's create the experiment from baseline. Okay. So we'll start from our baseline and just change the learning rate and the backbone family. Okay, so for backbone family, yeah. So we have the efficient net. All right. We'll start a custom grid search. So for learning rates, what we'll try? 0.005. Something smaller, something larger. Yes. So let's pick three learning rates. And then for backbone families, right. Here. We can choose ResNet. That's not. Maybe. and B0 again, right? Okay. So we can start our experiments. And while this runs, let's talk about what we think should be the step number 1.
So yeah, so the idea is that we will do it also iteratively, right? So we started now with this grid search with multiple learning rates and multiple backbone families that you selected. And it is not that bad choice. Usually learning rate is one of the most important parameters, but it goes hand to hand with a number of epochs, as kind of learning rate is the speed of your training, and number of epochs is kind of time, right? So how long you'd like to train the models. And it means that usually, if you're trying to tune learning rate, it is also better to tune it together with epochs. So if you're, for example, using a smaller learning rate, then maybe you need to train for a longer time. Or on the other hand, if you're like using very large learning rate, then maybe you need to use only a couple of epochs. And usually there are good kind of ranges for the epochs for this fine-tuning stuff is about from 2 to 10. So you don't have to train like for 50 epochs or like for 100 epochs, because we're already starting with the pre-trained models. So they were already pre-trained on like large ImageNet, for example, dataset. And that is why like having 2 to 10 epochs is enough to achieve good results. And for the learning rate, it is really tricky because different backbones need different learning rates. So for example, now we have selected like different efficient nets, ResNet, dense-net, and usually they have like this similar range of from 1 to the power minus 4 to 1 to the power minus 3, somewhere there, and we selected 3 values from this range. However, if you want to use some kind of like recent vision transformers or some other architectures, the learning rate might be much lower, and you might need to adjust it and like for the order of magnitude. So it really depends on the architecture you use. But usually, as I said, it is better to tune learning rate and number of epochs together. And another thing to note here is that we are assuming that the batch size is fixed, because if you change the batch size, and batch size is a kind of like the number of images we are passing for a single step. So for a single like update of the weights, we are making this small batch of the images. And like it depends on their learning rate, what will be our progression. So for example, if we have a fixed learning rate of 1 to the power minus 3, and then we have batches of 16 and 32, then it means that for a single same learning rate, we'll make different step sizes. So it will be either 16 or 32. And that is why there is a general rule that if you are adjusting the batch size, for example, if you are out of memory on your GPU, or you'd like to try some like smaller or larger batch sizes, then it is better to also adjust linearly your learning rate. So if you're like reducing the batch size by a factor of 2, then it is always better to reduce your learning rate also by a factor of 2. And it kind of allows us to compare these two models on a single scale, and it will allow us to tune models better. All right, so yeah, so we can probably go back to the experiments that we've run. So we have these 12 experiments, and they're still running, so some of them are already getting some results. So let's see what is the current best one. All right, so, and what was our reference? What was their baseline model score? It's probably outside of this project. All right, so we're already getting some better results, right? So there was one experiment with 815. And what was there? I guess it was efficient net, right? Yeah, it is efficient net V1, right? So yeah, so sometimes it is always hard to tell what will be the best architecture, right? So it is always a trial and error. And there are some kind of like general architectures that work better, and this EfficientNet v2 is kind of like currently the state of the art for the ImageNet dataset. But as long as you're trying to fine-tune it on your particular problem, it might happen then that it works worse than some like older architectures, or some simpler architectures. So it really depends on your problem. And here also in the tool we can compare the experiments, right? So we can like select our best experiment and maybe our baseline experiment, something like this. And we can see these charts that we have seen before all together. Right, so here you could see this charts together. Our orange line is our baseline experiment, and blue line is the one that is like currently the best ones that we've got. So as you can see, they use the same learning rate, right? So the learning rate was the same for both experiments. And on the top right, we see their train losses. So the idea is that here we are showing how well the model is fitting our train data. But it is not actually the sign of the model performance, right? Because we would like to evaluate the model on the validation data set. That is why on the like bottom left, we have a chart with a validation loss. And usually, the lower the loss, the better. And in this case, we're using this cross-entropy loss. So just evaluating the probabilities of each class, right? And then the lower it is, the better. And on the bottom right, we have the metric. So it is our F1 metric. And you could see here that it is like slightly better throughout the whole like training process, right? So we have like almost all the epochs for this efficient net V1 better than V2. And yeah, let's go back to the project. Yeah, we're almost done, so we have two more. Yeah, I mean, like probably let's go to the experiments and start some new stuff there. All right, we have two more. Is there anything better? Yeah, it's still the best. So yeah, so let's assume that we'll pick up this efficient net for the next experiments, and we will use the same learning rate, right? So tuning the learning rate didn't help us, so only another family of the backbone helped us a bit. And what we will do now is we'll make another poll where now you would need to select another like round of tuning. So what would you tune next? So now we have like efficient net V1. We have the same learning rate, and what would you tune next to improve their model performance now? So yeah, so you need to go to slide again. I'm also bad at jokes, so Martin. So it should have updated the poll now, so it should be fresh. And just to give a brief recap, right? So we have this like number of epochs learning rate, that is we already discussed. The backbone family, we also already tuned it a bit, right? Then we have backbone size. It means that we can go larger and we can use larger architectures of the same family. Then dropout and pooling are kind of like responsible for their fully connected layer we have in the end, and they like are responsible for some regularization technique. And another thing that is responsible for regularization is augmentations. So it is like these random transformations we are applying to the images. All right, so now number of epochs is going up together with pooling. And backbone size, all right. So you don't believe into augmentations, I guess. So I think we are done, right? All right. Yeah, so maybe you can take a mic and start this experiment.
Okay, so you've selected to tune backbone size and poolings. So we'll start with our current best with what we already have. So let's see if the last one finished. So what's the best validation score? It's still the one we already had. So we'll start from there. And we'll create a new experiment that will have, it was the size of the backbone, right? And it was the pooling. So we'll go custom grid. So let's see the sizes. So we'll try what B3. Now we're at V3 in EfficientNet V1. Mm-hmm. All right. Can I comment?
I can take it. So basically here we have a predefined list of architectures, but also it is pretty dynamic, so we support like hundreds of different architectures that you can just type in. So there is a library called TIMM, T-I-M-M. It is a storage of pre-trained PyTorch models that you can use. And there in this library, like it is fully open sourced. And you can specify any backbone from that library. And here we support like these hundreds of backbones. So we selected 0, 3, and 5, right? So it is just three different sizes of the backbone, and also have a pool in there. Yeah, and so for the pooling, as I said, it is their settings that is between our backbone and our fully connected layer. So here we're predicting 20 classes. So the last layer has 20 outputs. And in between, we have a fully connected layer that should kind of like connect all their combinations of two fully connected layers. And what we do is first we start with the images, right? And gradually in like CNN networks, in convolutional neural networks, the images are slowly decreasing. But in the end, you still have like this kind of like square image. But what we'd like to do, we'd like to kind of flatten this image into a single vector. And there are different approaches to do it. So the one is just like average. So we just take the global average over all this kind of pixels that we have in the image and get it for each channel. Another approach is like max pooling, and also have what is like gem pooling. Yes, so it is kind of a combination of average and max poolings that has kind of like trainable parameters of a weighted average and max poolings. So yeah, so let's see how it goes. Yeah, and while it is running, I will talk about our suggestion for the next step. So actually, after this first step, once we have like some tuned parameters for the number of epochs and learning rate, it is usually a good idea to start doing augmentation tuning. And the idea here is that usually your data sets are small, right? In this case, we also have only 2,000 images, so it is pretty small for 20 classes. So it is only 100 samples per class. And it might be a good idea to apply some transformations to your images, some random transformations, in order to kind of artificially increase your data set size. And these transformations might be different. So on the one hand, as Martin already mentioned today, it could be some simple like geometrical transformations like horizontal flips, vertical flips, or some shifts or rotations the images a bit. And it already allows you to kind of like build a better generalizable model in order to kind of enrich your original data set. And another type of augmentations is called mix augmentations. And here on the slide, you see the examples of mix up and cut mix. So in the middle is their image of mix up. So what it is doing is we're just taking two images of different classes. We're overlaying these images one into another. And instead of having like hard labels that it was class 1, class 2, we'll have soft labels. So it will say that 50% of this image is like class 1, and 50% of this image is class 2. And this percentage depends on the kind of the weights of their images in this mix. And it sounds a bit tricky, right? That we kind of like, yeah, and it looks really bad, right? That we're just combining like two images together. And it seems like a nonsense, but it allows the model to train this kind of like soft relationships between the images. And instead of training only on hard labels, we're also mixing the images together. So it is mixed up in the middle. And also on the right, there is a cut mix. And it is also an idea of mixing two images together into a single image. But in this case, instead of like overlaying one image into another, what we do is we actually like cutting one part of one image and pasting it into the same kind of location of another image. And it allows us to also combine two images together. And in this case, you could see that sometimes it can even make sense that some part of the image will be from one product, for example, and another one will be from another product. And then the model should learn that 50% of this image is from one class and 50% from another. And all these techniques are used for the regularization. And their idea of regularization is to kind of reduce the overfitting of the model and try to allow to train longer. So it means that now, once we have these harder examples for the model, it will take more time for the models to train. And potentially, we might obtain better results by like enriching our data with these augmented images. All right, so let's go to their to our results. So it is still running. So now it will take some time, right? Do you have any better results so far? Yeah. Sorry.
Okay, so we have one result that is better. And it is, so what's the difference here? Yeah, it is the same. So it seems like it's just a randomness because it might be a different seed, but the settings seems to match exactly the same settings we had before. Let's wait a while. So we have 5 finished experiments, 1 is running. Okay, so in the meanwhile, I'll show an example of the min-max augmentations that we have done separately, right? So let me find some example. Hard mix, okay. So here in the tool, we can have a look at different examples. So one are how does the data that comes to the model look like? So here you can actually see that first of all there's some cropping, right? There's some mixing. You can see here that we have a bunch of, so the original image is overlaid with another image, and there are also missing pieces. The label is also fused, so we can see that this has 24% of group 46 and 75% of group 198. So this is what the mix-up augmentation would look like. Yes. By the way, in our tool, we can also see some demonstrations of how well is the model doing. So we can see the loss along with the original images, and we can see the images with the best and the worst performance. So this way we can see if maybe there are some cases where it's really easy. So obviously, it seems like suitcases are quite easy for our model because they look like boxes. Okay, let's see how our experiments are doing. So we already have 8 finished experiments, so only 1 experiment is running so far. Let's see if we were able to improve our score. Yes, we were. Nice. So let's see. So now our F1 score is 8.225. So originally our baseline was at 0.795. And what were the changes that helped us? It was the increasing the size from B1 to B3. So we have that. So it seems like, and I guess we could say that usually the larger backbones behave better than the smaller ones. Okay, we have all our experiments are finished now. So far, still the best one is architecture B3. And the pooling, the average pooling worked the best. So the pooling did not really change anything. So now we can have a last round of tuning. So now you can choose, you just choose one parameter, or I think you can just choose one last parameter to try, and we can try that. And then after that, we'll compare your best model with whatever we've created in-house. Okay, so it seems like dropout is the favorite here. Okay, so let's try that and mix augmentations. So I guess I can take the best model we have and try out mix augmentations and dropout as well.
And maybe we can increase the image size a bit, so there is, but it is not that popular. Yeah, so usually, yeah, let's start some experiments and we'll talk about our last step. So we'll start with the best experiment so far. So it was like efficient net B3 with their average pooling. Yeah, and we probably need some grid search for the dropout. So initially the probability is 0, so we can try like, yeah, probably 0.3, 0.1, 0.3, maybe 0.3 is enough. And the second parameter was dropout and mix augmentations, right? So we can probably try both mix up and cut mix, I think. So this mix up and cut mix that we discussed, and maybe let's directly increase the image sizes a bit. So if you scroll up, yeah, let's maybe try to increase it a bit, like maybe to 348, 384. Sorry. Yeah, let's make it run. Yeah, and go back to the slides. So for our last step, what we are suggesting usually is to increase their model complexity and their like input complexity. So this time, like once you have some kind of like pretty good predefined settings before, and we used there some quick and small models, right, to tune the parameters. But once we're satisfied with these results, what we can do is we can try to run longer experiments, and usually it means larger architectures and larger image size. So you have already tried to increase the complexity on the previous step, which is already good, right? So we try to go deeper and try deeper networks. But another thing that's usually helpful is their image size. And the idea is that usually if you have like, for example, 1000 by 1000 pixel images, as we have here in our dataset, sometimes it is usually better to go up. So we started with only 224 by 224 images, and it might lose some information while we're resizing the images to this smaller size. And if you go, for example, to 512 to 512, it might increase your kind of memory footprint. It will train longer, but it might produce better results because you're providing more information to the model and you're resizing to the larger size. And for their like backbones, we're usually starting with a kind of like same family of the backbone. So in this case, it was efficient net v2. So we would first try to tune this efficient net v2 with like larger architectures. And it is what you did with efficient net v1, right? So we went from b0 to b3, and it allowed us to produce a bit better results. And the tricky part here is that even for this same family architecture, even for very similar settings, sometimes you need to retune the model. What retuning means? It means that you need to maybe adjust learning rate and number of epochs again, because with the larger architectures, maybe it is like easier to overfit to our dataset. That is why you need to, again, either to increase or decrease your learning rate or decrease or increase the number of epochs. And this is a tricky part, and it is like this infinity signs that we had in the very beginning, that it is kind of endless process, because for each step now you have too many like degrees of freedom that like might affect your results. And it is always better not to run a single experiment that tries a single experiment, but rather to run like multiple experiments with like similar settings, and try to retune this learning rate and epochs and see if they can have effect and produce better results. And that is why like usually the first part is pretty simple, right? To build this baseline model and obtain good results. But once you want to squeeze their like best performance out of your dataset, out of your model, it's getting tricky, and you need to run a lot of experiments. And yeah, let's see if we have our experiments finished and try to compare the results. All right, so we have one still running, and while it is running, we can go to the next slide there. So we will not tune models any longer, right? So what we will do is we will compare the models afterwards, once your model is finished, and we will compare your model with our best model. But on top of it, once you have like this final model trained and you're happy with its results, and you would like to kind of deploy it to the production environment, there are still a couple of tricks that you can apply during the inference. And inference means that it is a process when we are running the predictions on the new test data set. So these tricks are applied not during the training process, so the training is done, but still you can squeeze some performance from the inference. And the first idea is to retrain the model on the full data. So what we were doing so far, we were like kind of using this k-fold cross-validation, where we would split the data into like equal parts, and then leave one part out and evaluate the performance on this part. However, once you have like you're happy with the results, there is no need to evaluate your model any longer. What you can do is you can combine all your data together and retrain the model on the full data. And it will allow you to utilize like 20% more of the data, and it might produce better results on your like hidden test data set, for example. So it is one trick. Another trick is blending, and it is pretty frequently used in the Kaggle competitions. And the idea here is that we're ensembling multiple models together. So instead of having just one single model for the performance, we might combine outputs of two models. And then, for example, average probabilities of classes for two models. And as a result, usually it produces better performance. And the reason for this is that models are kind of learning different parts of the data set. And potentially, one model is good at one part of the images, another is good at another part of the images. And once you combine like their base kind of knowledge, then we can obtain a better result from the ensemble. And one last thing that is also interesting is so-called test time augmentations. So far we discussed only like these train time augmentations where you change your images during the model training. However, what you can do is you can run inference through your original test images, and also you can run inference through the test images that are horizontally flipped. So instead of like having the same images, we might have a bit different images now, and we can average the predictions of our original test image and this flipped test image. And then it would also allow us to like obtain a better generalizable model, because we are not doing a single predictions, but we are doing multiple predictions. All right, so let's now go to the experiments and run the final inference.
Okay, so the validation metric for the best model now is 0.87, which is much higher. And we achieved it by 0 dropout, so dropout was not used at all, and using the mix-up augmentation and the larger image size, which is quite important. Okay, so now we can do the inference on the test data. So we'll go to predict data. Last round, yes, this is the one. And we'll use this data set and the test CSV. Everything else is set. Here are our results. So our test metric was 0.823. So let's see what the models that we get here today will score. So we're almost there. It's the suspense. Nice. So we managed to create a better model in here with a test metric of 0.827. So good job, everyone. Okay, so once we have our model, we can see, right. We can see some statistics on the test and the best and worst performance. So what seems to be the case? Okay, seems like the worst for our models are shoes for some reason. So this might suggest we might want to get more data of shoes. Okay, let's go back to the slides now. Okay, so this is all for this first part of the talk, so thank you very much. We will invite Adam here, who will talk about his experience with the program of cooperation with students, and then we'll have some question and answering.
Yeah, since you outperform our guys here, so maybe we can talk more about cooperation with you. First, maybe I will start with a question. Is there anybody familiar with spolupráce s průmyslem, or the SSP cooperation with industry, or something like that. I didn't prepare any fancy Slido, but you can just raise your hand as a caveman. No one familiar. Yeah, two guys. Yeah, great. So for those you that don't know, I will stand here maybe. It's a brilliant way how to cooperate with us, or not only with us, but with the partners of CTU. The question that you might ask yourself is how to find some thesis assignment, and maybe you are looking for a part-time job, and you don't want to create something just for a thesis, but maybe something that someone need or maybe could use in the future. So basically, if you want to create a real-world contribution as your thesis, so you can use the cooperation with industry program, and it's a good way how to get not just A from your final, but a lot of stocks there has also some reward and these stuff. So yeah, it's a good way how to gain experience and start your future career and get mentor from the industry that you are interested in. So yeah. Personally, I have cooperated on both my thesis with industry, and successful cooperation on my master's led me into the H2O company, and my motivation was to create something that not going to be directly in the archive, but I want to contribute on the real problem. Also, I want to have good supervision on the thesis. You may be heard about the supervisors that don't answer your emails or whatever. So I would like to avoid it and try to get some motivated supervisor who cares about the thesis as much as I do, maybe sometimes even more. And yeah, we can turn. Yeah, great. So what I did, I have implemented brand new algorithm into a H2O open source platform. The lecture here was mostly about the hydrogen torch, but H2O has more products, and one of the products is open source machine learning platform for distributed machine learning, and it's actually the first product of this company that started the whole H2O. And it's open source, so it's great for students to cooperate with, because their code can be seen by anybody, and anybody can complain about it. So it's great. So my assignment was to implement extended isolation forest. It's a algorithm for anomaly detection that was presented in 2018. And I don't want to bother you with the details of the thesis, but in short, the assignment was to create the pseudocode on the left picture into Python code on the right picture in the distributed environment, and be sure that everything is running properly. And you can have more info in the link there. So the most challenging about this cooperation was to dive into anomaly detection, which I knew nothing about, and also dive into the big code base of H2O. So yeah, can. How the cooperation look like, and how the cooperation will look like for you if you decide to cooperate with us. So the start, it's pretty easy. You just can contact us on spolupráce s průmyslem or directly in COFIT, and we will meet each other and talk about your skills and preferences and time management if you plan to finish in 2 months or in 1 year. It's pretty important for us. And if the expectations are met, we can start directly to cooperate with us. It's everything prepared. We just need to have a handshake with you, and we can start. I actually have been on both sides. I was cooperating as a student and as a supervisor, so I know that H2O mostly care about proactivity from you, so you will get some initial sources and some papers that you need to go through, and it's up to you to share with us your struggle and ask for consultation. And currently we also offer some part-time jobs, so if you are fancy to cooperate with us or with these 2 guys and have a lunch with them, you feel free to ask. And what cooperation give to me and what can give to you, it's experience in contributing into the large and well-known open source platform, and last but not least, master diploma, job, and mentor from the industry. So feel free to connect with us, and thank you for your attention.
So thank you. And now if you have any questions, please post them to Slido. Or, I mean...
Can I ask, have you actually used some of the new generative models like Stable Diffusion or Stargam for generating data for pre-training models?
So the thing is, we as a company provide you the software. We don't have any data. And therefore, no, we don't use this for creating a data, because the data is always the customer's thing, and we never see or touch customer data. That's why also people like to use us, because we don't have a look at what they use it for. I mean, we have some basic idea, but no, we don't use generative models to build your data, but you can try it, and maybe once we will. Thank you.
But yeah, but it is currently the most frequent question we are hearing also on the customer calls. So each customer call now starts with this question, like, do you have generative AI or do you have any kind of generative models? Yeah, no, unfortunately our answer is no, and yeah, and they're becoming disappointed. So yeah, so it is a pretty high topic now. And from like our past experience, even in these like Kaggle competitions, there are sometimes very limited data sets, right, where you have like only like a handful of examples, and people are trying to use the synthetic data to generate more images and try to like generalize models better. But the issue with these generative like models is that all the information is coming from the same set of small set of images, and usually it is not helpful to generalize. So if we are talking about model performance, it is hard to squeeze more kind of information from the data set you have, and that is why usually it is not helpful in this sense. All right, there is another question in Slido, right? So in Hydrogen Torch, do you build on top of open source frameworks such as MLflow, TensorBoard? Yeah, this is a good question. So firstly, we are building it on top of PyTorch. So it is like this deep learning framework, right? That is pretty famous. And yes, as our name suggests, it's Hydrogen Torch, right? So it is built on top of PyTorch. And apart from using PyTorch, we also provide some tools. And actually, like one of the things that you mentioned here, MLflow. And MLflow we are using for the model deployment. So actually, once you have trained the model, you can download their model either as a usual PyTorch artifact with the model weights, or you can download the MLflow artifact. It is kind of like a packaged model that you can deploy anywhere, like as a REST API service, for example. And we are using MLflow. And TensorBoard is a tool for tracking your experiments. So the idea of this tool is that you can like compare experiments there, right, and track all your experiments. And as you have seen today, inside our UI, we have some functionalities to compare experiments between each other. But also we have an integration with Neptune. I don't know if you have heard about it. It is Neptune.ai. And it is kind of like a fancier version of TensorBoard. So it is pretty frequently used now for their tracking of the experiments. And it is not tied to TensorFlow or to any other tool. So you can like log there anything. But this Neptune AI is what I would suggest probably. Right. Yeah. All right. So the next question is: do you use a GPT for coding? So actually, like I'm personally a very kind of skeptical about this whole generative AI stuff, and I kind of like I can see the value, right? But I do not trust it. So as we all know, it is making errors, and it is hard to put it into the like kind of production without supervision. And the same holds for this coding, right? So I've tried it once, but you need to like be aware that it's making errors, and you still need to review the code. So it makes things faster, but at the same time it needs more attention, and sometimes like I don't trust it. So maybe others have better experience with it. All right. Yeah, but actually I had a chat with ChatGPT yesterday on the topic. It was some like a machine learning related topic, and like to write like a code snippet, and it looked like pretty well. So I mean, like if you have a supervision on top of it, yeah, it is really nice. All right. Any other questions? Maybe not through Slido, but just raise your hands and yeah, please go ahead. All right. So yeah, thanks again. Thanks for attending it. And yeah, hopefully it was useful for you. And feel free also, as Adam mentioned, feel free to reach out to us. So we have like, probably haven't left any emails, right? But you can easily find us. And we have a nice office in Prague, and please go and meet us there. Yeah, and we'll be on Coffee, right. So we'll be on Coffee, and yeah, you can meet us there. Thanks again.